Howdy, in this video we're going to go over chapter 14. It's on rolling element bearings. So the objectives for this video lecture are going to be to understand the difference between sliding bearing and rolling element bearing. 2, to familiarize with the nomenclature of rolling element bearing. And 3, understand and apply bearing selection criteria. So first, let's discuss the difference between sliding bearing and rolling element bearings. On the picture on the left, we have the sliding bearings. The white circle here is denoting a shaft. The light blue ring is going to be the bearing, and then in dark blue is going to be your lubricant, usually oil. And so what happens in sliding bearings, as you can see here, after they've been sitting, I mean, if it's not been rotating or they've been sitting there for a while, the shaft is gonna like move and it's gonna displace the oil around it away. And so right now, as the shaft is making contact with the bearing, we can calculate those contact stresses if we so wanted to. But what's important here is that when this shaft starts spinning, you're gonna have metal to metal contact or shaft to bearing contact until there's enough revolutions on this shaft that moves the oil around. And so eventually what will happen is the shaft is going to be riding on a very thin film of oil, and they're no longer going to be touching each other, which means there's going to be very minimal to nowhere once this is started going. But it takes some couple of turns for this to get going and to have this lubrication that's going to protect the bearing. And so the sliding bearings are called sliding bearings because we have to, you have members sliding past each other, right? And yes, you have some sliding friction, which is a little bit high initially, but after a couple of rotations, you have the film that sliding friction is gonna reduce. Again, when they're no longer touching and you got the film, the essential, the wear rates are very small. Rolling element bearings, on the other hand, they look something like this. So they have something that is going to roll. In this case, we have some ball bearings. And so you're going to have an inner ring and an outer ring. And as the shaft is rotated and the shaft will be fixed to this inner ring, what's going to happen is that these ball bearings are just going to roll. That's why these types of bearings are called rolling element bearings. And so here what you're doing is that in the rolling element bearing, you're substituting the sliding friction from the sliding bearing by a rolling friction. And this can have some advantages and disadvantages over the sliding bearing. Now, rolling element bearings are going to come with low energy losses. They're going to have low starting friction when compared to the sliding bearings. We have here the coefficient of rolling friction to be between 0.001 to 0.005. So these bearings are going to be good for applications that have high starting loads. They're going to usually be low maintenance or no maintenance. However, these rolling element bearings also have some weaknesses. And one of the weaknesses is that because you have very small areas contacting between the rolling element and the rings, this is going to lead to high stresses. So this is one of the reasons why these rolling element bearings are going to be made of very high strength, high hardness material. And also we must use them below the static load capacity to avoid Brinelling. So each of the bearings is going to come with a static load, how much force you can put before you can permanently deform the bearing, which is called Brinelling. I'll show you a picture in the next slide. And also these bearings are not going to do very well at very high speeds because high rotation speeds are going to lead to the rapid accumulation of fatigue cycles. Again, you're going to have this ball that it's rolling, right? So every time it does a full circle, it's going to see the stresses, a full stress reversal on the stresses, right? And as it's rotating, these are rolling, so you can accumulate very high number of fatigue cycles quickly on the bearings. We talked about Brinelling, right? And we said, look, if you exceed the static capacity of the bearing, what's going to happen is that those rolling elements are going to cause high enough contact pressures, and remember the associated shear stresses, that they can lead to permanent deformation of the bearing. So this is what Brinelling means, and it's after the The term comes from the hardness test, the Brinell hardness test, where you have a spherical indenture. Um, so when we're designing with rolling element bearings, we have to be careful about the static loads. We also have to be careful about limiting high rotating speeds. We learned that lesson, I say we as engineers, we learned that lesson early on. Look here in the picture, I have a picture of an old car. Maybe you can tell me what brand it is. But if you're not familiar, it's a Bugatti. Specifically, it's a Type 35B. Anyways, these cars were like were the top of the line, one of the fastest cars that won like the races in 1925, 26, 27, 28, and 29, right? So there was nothing that would beat this car. And in the engine, inside the engine used a rolling element bearings again for the low coefficients of friction. However, the engine was like fairly efficient for the time. If you were to take one of those cars, they're only good for like 4,000 miles. Again, because by around the 3 to 4,000 mile mark, all the bearings inside have already accumulated so many fatigue cycles that they start failing and the engine just tears itself apart. That's why if you were to open up your car engine right now for a modern car, well, we did away with the rolling element bearings for the crankcase, for example, and now we have sliding bearings, which is this picture over here. Anyways, now we'll go over the nomenclature used to describe these bearings. Boxed in, I have important dimensions for the bearing, which is going to be the bore, which is the size of this hole where the shaft is going to go through. The width of the bearing, this one you care when it's time to design or to manufacture where the bearing is going to be pressed into, as well as the outside diameter. Now we look at some of the terms. We're going to have two rings. So you're going to have the inner ring, is this guy over here, and you're going to have the outer ring. Okay, so the sides of the rings themselves are going to be called faces. You're going to have the inner ring face, the outer ring face. In between the two rings, so sandwich in between, is going to be your rolling element, which in this case is this ball bearing. There might be some separators, so keeping one from rubbing to the next one. So that's the separators. And these ball bearings are going to ride in the inner ring race over here and the outer ring race. So that's where they're supposed to make contact. What else we have over here? We have a corner radius. These are called the shoulders, by the way. I'm sorry. So see how there's a curvature over here, which is keeping this bearing from like popping out like laterally. That's the shoulder, and it is keeping that bearing in place. What else do we see here? Snap ring groove. This is for installation. But pretty much you at least want to remember inner ring, the outer ring, the inner ring raceway, the outer ring raceway, and then the important dimensions: bore, outside diameter, and width. Now let's talk about the rolling element bearing types. Traditionally, people think about just a ball bearing, which is where you have a spherical rolling element, and a roller bearing, where you replace the sphere with a cylinder. I'll have some pictures in the next couple slides. So these are the main two difference between the two geometry-wise. And then you have them also classified depending on the loading. So you have radial bearings, thrust bearings, and angular or tapered bearings. And these are just, again, going to be based on which way they can take the loading. So more on that on the next slides. So here we have, again, a ball bearing and a roller bearing. That's what those cylinders look like. And these are meant to take primarily radial loads. See, in this direction over here. The other type of bearing is a thrust or an axial bearing. So these are going to take loads that are going to be like oriented along the axis of the shaft. So you remember when we did the statics problems, we said, oh, we have journal bearings and we have thrust bearings. So the previous picture for the radial bearing, those are what we typically call the journal bearings in your statics. It means the same thing. They're just taking radial loads. If a bearing capability to take the thrust loads, right? Then it's a thrust bearing or a thrust, yeah, thrust bearing, sorry. So anyway, how do I do it? Look at the way the geometry changes. So now instead of having an inner and an outer ring, right, we have in this case like you want to call like a right hand and a left hand. Anyways, we can see we can transfer a lot of load in that direction, no problemo. And we can do it with the ball bearing and with the roller bearing. We also have angular contact bearings. So these are going to be in between the two. So these are going to be bearings that can take a radial load, but some thrust load at the same time. How do we do it? Well, look at how this guy is machined. The picture's not very clear, but maybe we can see it better with the roller bearing over here. See how those bearings are, well, for one, they're tapered, and two, they're at an angle. See, they're not like horizontal or vertical, but they're at an angle. These types of bearings, again, are going to take radial loads and thrust loads. So I guess to be more technically correct, if we go back to like your statics problems, there's the journal bearings and the thrust bearings. Whenever that term thrust bearing came about, usually in application, the bearings that we're using is the angular, because again, it's going to take radial and thrust load at the same time. If we remember the picture from the thrust bearing, right, of the ones in the previous slides, those bearings cannot take, or they can take very little radial loads. So next is we're going to talk a little bit about bearing design. Just note that some of the things that factor into designing bearings properly, right, are going to be the contact stresses, are going to be the fatigues, right? And so it's although it's a simple, right, you have some spheres and some rings, you might think it's simple, but if you really go in detail, it's very sophisticated and specialized. So the goal of this presentation in the book is not for you to be able to design the bearing, but instead we're going to teach you how to spec or pick out a bearing for an application. So how to pick the right one. Similar to the bolts, right? We didn't teach you all the engineering that went into designing the bolts and why the angles of the threads. I mean, we talked about it a little bit, but usually you're not specing a bolt. You're not specifying your own thread patterns. The goal for this class is just to be able to, from standard bolt sizes, pick a bolt. Same thing here for the bearing. From whatever is available, let's pick the best one for the application. So just like we went through the tables with the bolt sizes and the other table telling you the bolt grades or classes, the information and bearings are usually published in catalogs. And the bearings themselves are going to be identified by a bearing number. So instead of saying, oh, I need a 40 millimeter bearing, you're going to need to know how to determine the bearing number. The bearing number looks something like this here below. Where the number itself might be some letters and mixture of numbers, okay? So the first character over here is going to give the series of the bearing. In this case, we have a letter L, and an L is telling us that we have an extra light duty bearing. We could replace this letter L by a number 2. In that case, it would mean we would have a light duty bearing. And if the L was a 3, it would designate a medium duty bearing. And these are the 3 ones that are available in the catalogs that we include on your Machine Elements book. The next 2 characters are going over here are gonna help us determine the bore diameter. And I say help us because it's not a direct measurement. So if you see here 0.8, it doesn't mean that the bore diameter is gonna be 8. In actuality, what you do is you take this number, you multiply it times 5, right? So 8 times 5 is 40. And this guy actually is telling us that we have an extra light duty bearing that has a 40 millimeter bore diameter, right? And this holds true for bearings that are 20 millimeters or larger, right? So for any bearing with 20 millimeters or larger, the bore diameter is just going to be 5 times the last 2 digits. Or you can think of it in reverse. Like if you have, for example, if you need a bearing with a 50 millimeter diameter, right? You take that 50, you're going to divide by 5, that gives you 10. So that would be a 10. If it was an extra light duty, then it would be an L10 bearing. So what do we do with bearings that are less than 20 millimeters in diameter? I'll show you in the next couple of slides. But first, now we're going to go into table 14.2, I'm sorry. And this is going to give us the rated load capacities for the different series of the bearings. And what you're going to see is that we're going to have the different types of bearings. We have the radial ball bearing, right? This is meant to take mostly radial loads. Can take some thrust loads, and we'll teach you how many or how much and how to design with that in the next couple of slides. But anyways, we have radial ball bearings. We have the angular, right? These are the Goldilocks bearings that can take the radial and the thrust. And then we have the roller over here. We have those cylinders. So I didn't ask you before, but why do you think we have ball and we have roller bearings? Okay, so if you thought about, well, what's different between the two is one is a sphere and one is a cylinder. Remember your equations for contact stresses, right? When you have a ball bearing, you have a point load. So the contact pressures or stresses are always going to be higher for a ball bearing than a roller bearing, because the roller can distribute those stresses over some line or rectangular cross-sectional area. So you're going to see very quickly that, for example, if you have a bore diameter here of 20, if you have a ball bearing, they can take between 2 to 5 kilonewtons, depending on the series of the bearing. The roller, which is the cylinder, starts at 3.3. It can go all the way to 6, again because of the higher area. So some of the trends to notice here is as the bore diameter increases, the capacity, the load bearing capacity for that bearing is going to increase. And that's true for any series. If you take a look here at the L series, which again, here below it tells you XLT or extra light series, right? We see as the bore increases, the load increases. Here is what the 200 series or a light duty, right? Again, as the bore diameter increases, the load increases. And remember, the 300 is meant to designate the medium duty series. I do want to point out, I don't want to forget this one, that these rated capacities are going to be good for, they're going to be good for 90 times 10 to the 6 revolutions, right? So notice LR is what we call this rated life of the bearing. The life of a bearing is not given in time because why? Well, because depending on the speed, right, the time is gonna either go down or go up. The faster the bearing is spinning, the quicker it's gonna fail. So instead what we give it is the rated life is in revolutions. So 9 times 10 to the 6 revolutions. So what they're telling us here is any one of these bearings can take that set load. For example, a radial ball bearing with a 20 millimeter bore diameter can take 5.3 kilonewtons of load. And it can handle that for 90 times 10 to the 6 revolutions, which is roughly about 3,000 hours of continuous 500 RPM operation without any surface fatigue. So here I do want to remind you that the bearing tables provided are for 90 times 10 to the 6 or 9 times 10 to the 7 cycles, but these are for the bearings that are in your equation booklet. Once you go out to the field and you're picking bearings from the different suppliers, you want to make sure you double check with that bearing supplier or the bearing manufacturer to see what is the rated life that they're giving for that bearing, because the number might change from manufacturer to manufacturer. This table here is giving the bearing dimensions. So the previous table gave us the rating capacities, how much load we can put on a bearing, and we saw that they depended on the bore diameter. Now that previous table wasn't complete. The table is more than what I could show on the PowerPoint slide. And so is this one with the bearing dimensions. Okay, so this one is giving us, again, from the bearing number, bearing basic number, what is the bore, the outside diameter, and then these other dimensions over here. So remember we told you, look, if the bore diameter is 20 millimeters or higher, what you're gonna do is you're gonna take that bore diameter and divide by 5 to get that bearing number. And then it's like, okay, what do we do with bearings that are less than 20 millimeters? Well, just look at this table here. If the bore diameter is 10, then that's a 0, 0. If the bore diameter is a 12, then that's a 0, 1. If it's 15, then that's a 0, 2. Here I drew the line over here, right? So if it's 17, it's a 0, 3. And then with 20, 20 divided by 5 is 4. So here's where that rule now applies. So L04, 25 divided by 5 is 5. So we have 0, 5. Anyway, so if you ever forget that factor, right, or you're unsure, you can always look at the dimension tables and say, hey, I need a bearing that is 40 millimeters. What's the bearing number? Well, it's going to be a 0, 8. And so which one specifically? Remember, L is for extra light, 2 is for light, and 3 is for medium duty bearings. Again, what are these other columns? This is what they are, right? They're going to be here the outside diameter, the bore, this radius, this diameter over here of this shaft, and then DH over here is going to be the diameter of this hole and the width. So next is, now you know the bearing capacities, at least where to find those in the bearing dimensions. So now let's start talking about how we're going to select the bearing. And when you do, you're going to have to make some decisions as to the bearing type. If you want a ball, roller, an angular contact, the grade, the precision, which is related to the tolerances of the bearing, right? The higher the precision, the more expensive the bearing, but it's going to have less vibration, it's going to be less noisy, for example. As an engineer, maybe you will get to specify the lubricant that will be needed for the bearing, although some of these bearings are sealed with lubrication already incorporated, and so and they're designed in such a way that they're non-serviceable, so you can't go in there and say change lubrication. And this is going to come from their closure or their seals. We're also going to look into the load rating, specifically the static load capacity. So we want to make sure that when you pick a bearing, you never do exceed that static load to avoid Brinelli. The manufacturers will also give you the maximum speed that the bearing is good for. The speed is going to be more of a linear surface speed than a rotating one. So what this is going to translate for us is that it's going to be that small bearings are going to be able to operate at higher RPM than the larger bearings. What is this linear surface speed? Like if you imagine this bearing was a wheel and it's rotating, right? That is the linear speed. Like how much distance would it cover at those RPMs, right? And if you have like a very big wheel, even if it's spinning at a very low RPM, it's covering a lot of distance, has a very high surface speed. A small bearing, right, something with a very small circumference, if you want to think it that way, it can spin very fast, but it still doesn't cover a lot of linear distance. Okay, so higher, smaller bearings are going to be able to take the higher RPMs better. And then sometimes you might be able to specify a DN value. This DN value is, it's a factor that we use to specify suitable lubricants for the bearings. But again, most of the time when you buy a bearing nowadays, they come pre-sealed with the lubricant in there for life, for the life of the bearing. So let's go to other things that we have to consider for the bearing selection, and these are the ones that we're gonna use to pick the bearings actually. So the two equations in these slides are gonna serve as the baseline to help us determine two things: a capacity of the bearing and the life. Because when we're talking about bearings, there's two things that we can calculate. Either we know the life of the bearing, so we know how many revolutions we want that bearing to last, and we know how much load it can take. And so all we have to figure out is what size of bearing do we need so that it's good for that life. And so the size of the bearing, right, is going to come from that capacity. So that's the second formula. The first formula is maybe I have a bearing size, right, and I know the loads that the bearing can take. How much is that bearing going to be good for? That's the bearing life. So we're typically solving for either one of these two, and these are going to be the formulas. I say baseline formulas because we're going to add in the next couple of slides some other factors that are going to help us account for more information. But these are going to be the starting equations. So what are the terms? Anytime you see the L is going to be the life of the bearing. The life is going to be in revolutions for a bearing, so don't get that mistaken. Next we have this term which is LR. LR is the correspondent rated life. So it's the rated life. This is the 90 times 10 to the 6 value. Next is going to be C, which is the rated capacity, right? So if you have a bearing size, right, you go to the table, and depending if it's extra light, light, or medium duty, you're going to be able to determine that capacity. So this capacity is in units of usually kilonewtons. This is going to get divided by, for example, for life, by FR. FR is a radial load for that application. Okay, and then this gets multiplied, or I'm sorry, raised to this power of 3.33. If we're talking about the capacity formula, C reg is the required capacity. Again, this is going to tell us the bearing size indirectly. FR is going to be the radial load. L is going to be the life in revolutions. LR is a rated life, right? So look at this ratio, right? It's how much revolutions we want divided by how much that revolutions that bearing is good for, and then raised to the 0.3 power. And actually, I have these like as if they're two separate equations, but really it's the same equation, but here we solve for L, and on the bottom one we solve for C. So if you were to solve for C in this equation, for example, it would equal this one over here. And so the takeaway message here from this power is that the bearing life is going to be inversely proportional to the 10 by 3 power, or 3.333. That means that if you double the load on a bearing, it's going to reduce its life by a factor of about 10. Now what we're going to do is those previous equations, we're going to start adding or multiplying by some, multiplying by some factors to account for other things. So the first thing that we're going to account for is going to be reliability factors, is KR. And so the previous equations that were assuming that you wanted a bearing life or a bearing capacity with the standard life of the bearing, which is 90% survival, which means that only 10%, you'll see only 10% of failures. Now, if the application is critical and you want to reduce the number of failures from 10% to maybe 5%, or all the way to just 1%, where only 1 out of 100 bearings is going to fail during that rated life, for example, we need to multiply by this K factor, KR. So for 99% reliability, you're talking about a KR of I would just say 0.2 in this equation. Now, what is that doing? Well, look at where the factor is. For the rated life, if you have all the previous terms and then you multiply by 0.2, really you're saying it's only good for 20% of the original life. So what does that mean? Let's make some super dumb numbers. Let's say a bearing was good for 100 revolutions. Like, it's not unrealistic, but let's just say 100, just for the math. So at 100, it's good for 100 revolutions, and you'll see 10 out of 100 bearings fail. But if you only want to see one, then you would only have to limit that life to just 20 revolutions, or 20% of that. Again, that's for the life. So what we're doing is we're taking just a fraction of the revolutions and saying, oh, we're gonna put our seal of approval that it's only good for less life. If we look at the capacity required, that Kr factor is going to occur here at the denominator. So what it's going to end up doing is going to end up increasing the capacity required. So it's going to tell us that we're going to need a bearing much higher. Again, a bearing that is bigger can take more load. So by oversizing that bearing, we're ensuring that even at the less applied loads, less of the bearings are going to fail. The next thing is we said that, well, we have bearings that can take axial loading, radial loading, the radial, and then axial over here, or thrust loads. But what would happen, for example, if we take just a regular bearing meant for radial loads, like in this case of this roller element bearing, and then we put some sideways or axial loads. And what will happen is this rolling, the cylinders, for example, are going to start rubbing at the faces of those rollers. It's going to increase the friction, and it's going to effectively reduce the life of that bearing. So for these type of bearings, that thrust capacity is about 20% of the radial. You go higher, and then the service life is going to decrease very quickly. So again, whenever you need that capacity to carry some axial or thrust loads, we're going to go with tapered roller bearings over here, for example. These are meant to design sideways loads. You can see here by the angle that even if you push in this direction, we're just going to compress or sandwich these two surfaces, which again, this bearing is going to be good for an axial direction here towards the left, for example. If you need to secure the shaft so that it doesn't move either left or right, then we can use these double row bearings over here. So see how it has the two different angles. So each of the rolling elements oriented at the angles is going to take the loads in one direction and the other, right? And you can do so to limit the axial loads in both directions. Now, if you can get a bearing that is good enough size to support those axial loads, we can double up on those, so we can stack them until we have the enough capacity to keep from that shaft from moving sideways or destroying the bearings. So hopefully it's clear from the previous slides that, for example, if you have a radial bearing, right, those bearings are designed just to take radial loads. And if you start putting any sideways forcing or any thrust loads, their service life might decrease. So how do we actually account for that as engineers? Well, we have what we do is we calculate the ratio of the thrust load divided by the radial load. And depending on the value of that ratio, we do a couple of things. So if the thrust load is between 0, if the ratio is between 0 and 0.35, or another way to think of it is the thrust load between 0 and 35% of the radial load, then we do absolutely nothing. This FE is going to be an equivalent load, and what we're saying is, look, the load is so low that we're just going to assume that we're only seeing a radial load. And so this FE is going to be equal to FR, and that's the value that we use in the formula. If the ratio is any higher, if it's between 0.35 to 10, then we're going to correct with this formula here. And if the thrust load is even higher than that, so the ratio of the thrust load divided by the radial is greater than 10, then this equivalent force is just going to be 1.176 times the thrust load. So we are even going to forget about any radial load. That's how high that is. Anyways, if we look at the middle equation, right, this in parentheses is just going to give us a factor, right? So this factor is going to be greater than 1. See, 1 plus, and then we have 1.115 times the thrust load divided by the radial load minus 0.35. Again, so all this is doing over here, this is a factor that's going to be greater than 1. And it's just going to, basically what it means is, hey, the bearing is designed to carry radial load. Now we have some thrust. And if it falls in between this range, we're just going to design as if it's just seeing a higher amount of radial load over here. That's what that equivalent load is. And we can do this same type of corrections for angular bearings as well. Now notice the limits are going to change. When we look at the limits here for the thrust divided by the radial, that ratio, where a radial bearing, right, is only good up to 0.35. An angular bearing, that ratio can be all the way to 0.68, and still, right, we would only consider the radial load. Now, if that ratio is bigger, between 0.68 but less than 10, we would use this equation, which again, all it's doing is we're going to end up with a factor that is greater than 1, so it's upping up the radial load for us. If the ratio of the thrust load per radial load is much higher than 10, or greater than 10, I should say, then the equivalent load is just going to be 90% of the thrust load. Notice the difference between the two, between the radial and the ball bearings, right? Those limits are much higher for the angular bearing because these guys can take more of the thrust loads. And notice for the extreme cases where we have a whole lot more thrust loads than radial loads, see how the equivalent load for the angular is less than 1. It's about 91% of the thrust load, where the radial load is not designed to take the thrust load, right? It's greater than 1.176 the thrust load. The other thing that can happen is that bearing can be under a shock load, and this shock loading is going to effectively increase the nominal load on the bearing, and we're going to count with it with an application factor Ka. So here we have for the two types of bearings, a ball bearing, remember point contacts, and roller bearing, which is a line contact. And you can see here, if the loading is uniform and there's no impact, it's just 1. If the type of impact comes from just the meshing of the gear teeth or gearing, ball bearing is going to have a Ka of 1 to 1.3, where the roller, it's fine, like no change yet. If it's under, light impact, 1.2 to 1.5. If it's moderate, 1.5 to 2. If it's heavy, 2 to 3. And those for the ball bearings, and you can see those factors are going to be much lower for the roller bearings. So here, I will note that when you're going to do the homework, you're going to have to be paying attention to these keywords. So, oh, there's gearing and it's under light impact or heavy impact. So again, as you're reading those problem statements, that's what it means. So it's signaling you to come over here and pick an appropriate application factor. So now we end up with these two equations. This is the ones that we want to use. These equations are going to give us the life that we're going to get in a bearing, a number of revolutions, or the capacity, the size that we need for a bearing for it to last a certain life, again in revolutions, given factors such as reliability, equivalent force, which is accounting for any axial loading or thrust loading in addition to radial loads, as well as your Ka factor, which is accounting for any shock or impact loading on the bearing. And the top one gives us the life in revolutions. The bottom one gives us the capacity required, which in turn is going to tell us what size of bearing we need. Now, we mentioned life over here, for example. If we want to solve for how big that component needs to be, I need to tell it, well, how many revolutions I want it to last. And this is where table 14.4 comes in handy. This table is going to help us design or let us know what the design life should be for a bearing that is operating under various conditions. At the most extreme, we can have a bearing that is operating 24 hours a day, and where reliability is extreme important, right? So this means we cannot afford to shut the equipment down to do maintenance. They want us to design between 100 to 200,000 design hours or operating hours. If the machine works 8 hours a day, but not every day, only 14 to 20,000. If the machine is used intermittently, where service interruption doesn't matter or is of minor importance, then we want 4,000 to 8,000 hours. Now, again, we want the life in these equations to be in revolution, but this is in hours. So how do we do that? Well, let's say that machine is operating at 1,000 RPMs. 1,000 RPMs or 1,000 revolutions per minute, which would mean that in 1 hour, right, 1,000 RPMs in 1 hour is going to equal 60,000 revolutions. However, if we want to use it in a machine that is used intermittently, we can interrupt it. We want to design for 8,000 hours. So 60,000 revolutions in 1 hour times 8,000, this is going to give 480 million revolutions. So that's how many revolutions we would need to put over here. Again, that would be for a component that's operating at 1000 RPM, and it's going to be used intermittently over here. So we want it to be good again for 8,000 hours. Now let's say that bearing, if instead of being used in an application with intermittent use, if it was on a machine, again, operating at the same 1000 RPMs, but it has to do it 24 hours a day without any interruptions, with reliability of extreme importance, which is almost the same thing, right? Again, that bearing would be 1000 revolutions per minute. So we will multiply times 60 to get to 60,000 revolutions per hour. And then if we multiply times 200,000 hours that we want that thing to operate, that gives 1.2 times 10 to the 10, or roughly 12 billion revolutions that bearing has to endure. Just to add some perspective, 200 design life hours, right? We divide it by 24 to give us 1 day, and then we divide by 365. It's going to result in roughly 22.8 or almost 23 years of continuous operation without that bearing failing. Now remember, those equations, right, are, if we just put a standard KR of 1, that means only 10 out of 100 bearings are going to fail. If we want less, then we would increase even more this reliability factor. So now let's work through an example. In this example, they want us to select a ball bearing, which is going to go on a machine press, and that machine is supposed to operate continuously in one shift, so an 8 hours a day operation at 1800 RPM. Notice that shaft over here is under radial and thrust loads, which are 1.2 and 1.5 kilonewtons, and it will be under light to moderate impact. Now, when you hear the question, select a ball bearing, really they're telling you, or they're asking, what size of ball bearing should I use? So whenever somebody asks for a size, the way you're going to get the size for a ball bearing is by looking at the capacity, right? Because the size is going to determine the capacity of the bearing. So really they're telling you, hey, use this equation over here for the capacity and tell me the capacity in kilonewtons. And remember, ball bearings, we can get them as radial bearings. These are designed just to take radial loads, and angular bearings. So these are designed or better equipped to take thrust loads over here. You can see the internals a little bit, just roughly the geometry. It's how we have a big shoulder on one side and a very small shoulder on the other. So this guy can take the lateral forces over here, and you can see kind of the resultant of the two forces in this direction, radial plus thrust. Anyways, the angular is designed to take better the thrust loads. Anyway, so in this example, we're actually going to spec two radial bearings and angular bearings. Again, the formula that we're going to use is this one over here, where we need to calculate equivalent load, application constant, a life in revolutions, reliability factor. This is the rated life, and it all goes to the power of 0.3. I do want to mention here that in this example, right, they're telling us the radial load and the axial load. This would come from doing statics on that shaft and figuring out, for example, this would be from a thrust bearing, one that is capable to exert an axial reaction, and a radial one. So you would, if this was a complete example, right, we would be looking at a shaft, solving for the reaction forces at those bearings, and then with those information picking the actual size of the bearing, which is what we're going to do next. So Since we'll start with the radial bearing first. Again, we know it's spinning at 1,800 RPMs. The thrust load is 1.5 kilonewtons. The radial load is 1.2 kilonewtons. It's under light to moderate impact, and it's going to work 8 hours a day. So the first thing that we want to do, remember from our formula over here up on top, is we want to calculate the equivalent load. Now to calculate the equivalent load, it's going to depend on the ratio of thrust load per radial load. So when we go ahead and calculate the ratio of the thrust load, 1.5 divided by the radial load, 1.2, we get a ratio of 1.25. So that means, right, that ratio falls in this middle range over here. And so the equation for the equivalent force is just going to be the radial load multiplied by the quantity here in parentheses, which is 1 plus 1.115 times the ratio again of the thrust load per radial load minus 0.35. So when we go ahead and substitute the values here for the radial, the thrust and radial loads, we put it in this equation and we get an equivalent force of 2.4 kilonewtons. Now hopefully you can appreciate what this number means. We're picking a bearing off the shelf that is a radial bearing. So it's designed only to take radial loads and very little thrust loads. And so what we did is with this equation over here, we factored up, I guess, the radial load over here. So now we're saying, hey, this is the same thing as this bearing feeling 2.4, although in the radial it's only 1.2. So see, it's almost doubling the so-called radial load. Again, but we're calling that one equivalent load. Next, right, we want to solve for the application factor here, which is as a result of shock or impact loading. So we go to the table, and again, we're designing with a ball bearing in mind. In this case, it's a radial ball bearing. And they told us light to moderate impact. And we're like, okay, so what happened here? We have uniform gearing, light impact. They give us a range, moderate impact. There's a range over here, heavy. But because they want light to moderate in between, so that number in between is this 1.5. So we'll set our Ka value to 1.5. Ka equals 1.5. Next on this equation is we're going to head and solve for the life. This is how much revolutions the bearing should last. Remember, it's not in time, it's by revolutions. However, if you remember, this machine here for where this bearing is used for 8 hours a day. I'm going to assume that it's used every working day. So they give us a range here. We want to make sure that bearing is good between 20 to 30,000. I'll always get the bigger number, right? Because the more hours I design for, the more confident I'm going to be in my design. Okay, so the life here, we know it's operating at 1,800 revolutions per minute. So I'll multiply times 60. So I can have now revolutions per hour, because the minutes are going to cancel here. And then I'll multiply times 30, which is the upper range for the application that they want. So 30,000 hours. So now hours are going to cancel with hours. And you can see here that we're going to end up with the life of the bearing just in terms of revolutions. So we go ahead and plug all of this in the calculator, 1,800 times 60 times 30,000. This is going to give 3.24 times 10 to the 9 revolutions. So now we know the life that we want for that bearing in revolutions. Right, 3.24 times 10 to the 9. The next term in the equation is this Kr, or reliability factor. So when we read that question, I know I don't have the problem statement anymore. There was no mention of a reliability factor. So for this application, we're just going to stick to the standard reliability that of 90%. So we go over here with standard reliability 90%. This means you have to use a factor of Kr equals to just 1. If the problem had mentioned 95% reliability, 97, we wouldn't have to come over here to this curve and figure out what values over here we would need for Kr. Again, since there's no mention of reliability, we'll just use the standard reliability, 90%, or just 10% of the bearings are going to fail. So with the Kr value of 1.0, the last term on that equation is Lr. And hopefully you remember what this Lr means. Lr stands for the rated life for the bearing. This is the number that you're going to get from the manufacturer of the bearing. This is what the number that they use to tell you, okay, this bearing can take X quantity of load for this Lr, or number of revolutions. Because all the bearings in our machine elements booklet, they come from the same supplier. That supplier rated them, for a life of 90 times 10 to the 6 revolutions. So Lr is 90 times 10 to the 6. So now we have all the information. We can just plug in all these different values in the capacity equation. Again, Fe is 2.4, Ka is 1.5. Next is going to be next is going to be the life that we want in revolutions, 3.24 times 10 to the 9 revolutions, divided by reliability factor. This guy is unitless. And then the rated life of the bearing, which is 90 times 10 to the 6. Hopefully you can see in this equation that revolution is going to cancel here with revolution. So everything in here is unitless with the exception of the equivalent load in kilonewtons. So we plug all of this in the calculator. We have the capacity required is 10.55. So we need to select the bearing that can take 10.55 kilonewtons or more. Again, so we're after bearings that can take 10.55 kilonewtons. Remember in this table, there's a couple of bearing types. We have radial ball bearing, angular ball bearing, and roller. Right now we ran the calculations for the radial ball bearing. So all we're gonna do is go down the columns, right? And we want a bearing that can take 10.55 or bigger. And we got options, right? Because we have 3 different series of bearings: extra light, light, and medium duty. So if we go down the extra light column and we're looking for numbers greater than 10.5, we see here that the bearing with the bore diameter of 65 can take 9.10 kilonewtons. This is not enough. And the next bearing up, or bigger size, the 70, takes 11.6 kilonewtons. So this is enough. This number is bigger than the capacity that we require. So this would be the bearing that we would be selecting if we want a light duty bearing. Now we need to write that as a bearing number, the spec, remember. So the first character is from the series. This being an extra light, we're going to use the letter L. See this L00, we're going to use L. And then the other digits come from taking that bore diameter and dividing by 5. So 70 divided by 5 is 14. And so there we go. If we wanted an extra light duty bearing, we would use an L14. Now the problem didn't specify use light, extra light, or medium, right? So if we wanted extra light, it would be an L14. If we wanted to use a light bearing, again, we're looking for 10.55. So as we scroll down, we got 9.7, and this one's 12. This is the one that was gonna take it, right? It's a light duty bearing, so it has to start with 2, the bearing number, and then 55 divided by 5 is 11. So a 211 bearing could also work. Again, that would be a light duty bearing with a 55 millimeter bore diameter. If the problem specified medium duty or medium series, again, we would look for a value. This one here, 8.8, is not enough. 10.6 is just slightly above, so that fits perfectly, right? It's medium duty, so the first character is going to be a 3. And then the last 2, we get it from the bore diameter, so 35. Remember, always we divide by 5. 35 divided by 5 is 7, so we would use a 307 bearing. So these are 3 radial ball bearings that would work for that application. Next, let's go ahead and run the calculations for the angular ball bearing. You're going to see it's going to be almost the same thing. The general equation does not change here. We have to calculate equivalent load, application factor, reliability factor, right? The change is going to come here for the equivalent load. Now remember, an angular ball bearing is designed to take thrust loads better than a radial. So to calculate that equivalent load, we're going to do the same thing. We're going to calculate the ratio of thrust divided by radial. Remember that ratio was 1.25. And then we're going to look for which formula applies for the equivalent load. Well, 1.25 is this middle one again. But notice the formula is a little bit different. Hopefully you remember that from the previous slide. Anyway, so the formula calls for just putting the radial load, 1.2 kilonewtons, then multiplying it by 1 plus 0.87, and then multiply by the ratio of the thrust by the radial minus 0.68. Anyways, we plug all of this into the calculator and we get an equivalent load of 1.795 kilonewtons. Now hopefully you remember the other number was 2.4 something. For this one we just want 1.7, again because the thrust load does not affect too much of this bearing. If we're following along the equation, right, the next factor that we need is the application factor. Again, it's still working under light to moderate, so the value that's in between the two is 1.5, so Ka equals 1.5 like last time. And just like last time, we have to also specify the life in revolutions. It's still the machine that's working for 8 hours, so the calculation is exactly the same. The RPM of the bearing times 60 to convert to revolutions per hour times the number of hours that we want for that design life. So we get 3.24. The number doesn't change. It's the same one as the previous one. And we'll also assume a reliability factor of 1, which means we're just going to go with the standard reliability. We plug in all the values and equation over here for capacity, and it gives a capacity of 7.898 kilonewtons. So look at the difference. I have the values here for the previous one, just the radial ball bearing. If we want an angular one, because they can handle the thrust better, we need less capacity, just 7.8 kilonewtons. And just like in the case of this one, we're going to go to the columns now labeled for angular ball bearing, and we're looking for a bearing that has a capacity of at least 7.89. Right, so this one is 6.6, does not cut it. The next one, which is 9, is more than the 7.89 that we want. So this is a good bearing, right? This is a extra light duty. So the bearing number is going to start with the L. And the bore is 55, right? So divided by 5 is 11. We get L11. And so by now, probably you don't need me to repeat. But again, we're looking for 7.8. This is a good one, right? So it's a 235 divided by 5 is 7. So a 207 is a good bearing. And this is what a medium bearing would look like. So 7.8, right? 7.2 does not cut it. 8.8 is what we need. This is a medium duty, so the bearing number is going to start with a 3. And then 30 divided by 5 is 6, so a 306. Anyways, for that previous example, if we want a radial bearing, any of the ones on the left are going to work. If we want an angular ball bearing, then any one of that's right over here is going to work. Don't get too scared of what you're gonna do in the homework, and the homework will specify, give me a radial medium duty or angular light duty. So there will only be one correct answer. But that's generally it, the process. The only thing that we skipped here, and it's for the sake of saving time, is just doing the statics to figure out the reactions at the bearings. Once you have the reactions of the bearings, this is the process that you would follow. Again, here we've solved for what size of bearing we want, so that's the capacity. The other equation has all the same factors that we pick them in exactly the same ways, but in those cases we would be solving for an L, which would be a life in revolutions, given a certain size or capacity of a bearing. Oops, sorry. So I have a link here. I like to every once in a while put some videos in my class, usually like from old school videos, like from many decades ago, just so that you've seen the kind of the progress of the engineering and in the field. Um, Anyways, so feel free to copy the link and maybe watch this old video if you like. And so that's all I have for bearings. Hopefully the homework is going to show you a couple of little bit different scenarios so you can practice some more sizing bearings and determining how the lifespan of those bearings. Thank you for watching.